So, I hear you're all in Munich, but let's imagine you just arrived to the city for the very first time, and that you arrived to a new share flat, okay? So you get there with all your luggage, all your boxes, and you arrive to your new room. And what do you see? Well, it's empty. So you're in Bavaria, it's a Saturday, and you definitely have to get to Ikea before 8 p.m. Otherwise, no chance. And you have to get this done by today. So you go to the website of Ikea, and you already scroll and see all the things you want to buy. But there is something missing in this story. You need to measure the distance from the two walls. Otherwise, you don't know if all these things are going to fit. So you go there, you ask your new flatmate, and you say, do we have a ruler in the flat? And he's like, yeah, sure, we do have a ruler. Just go to this blue drawer that we have in our kitchen. So you go there, you open it, and this is what you see. This is literally, no joke, a picture of what we took for what we call in our VG the Bermuda Triangle. You can already think why this is the case. And here what you see is a lot, of course, of shopping bags, but here on the right, what you don't see is a lot of useless tools. But you can already imagine what I did not find, the ruler. So I had no ruler. So I am in this situation in which I definitely have to measure the distance between the walls. Lucky me, I am a physicist and actually an experimentalist. So I thought, I'm very used to try to measure things. So let's try to think of a way of measuring. I could use, for example, if I knew the distance of one of my steps, I could count how many of them fit between the walls. But what if I wanted to be more precise? I would have to shrink the size of this ruler. For example, I could use my shoe size, and then I could count 1, 2, 3. Then I would go online, Google the shoe model, and try to see and measure. Actually, I would know the distance and just multiply. And like this, I could measure the size. But what happens when you want to measure tinier things? You all know the ruler. The distance of a ruler, the smaller division you can measure or use, is a millimeter. Some of you may be familiar with a caliper. It's another tool that actually measures 100 times smaller than a millimeter. But what comes next? So, as in the lab, we do this all the time. We measure tiny things. And the ruler we use is light. And this is what I'm going to talk about tonight. So, what is light, first of all? So, light is a wave. And you may all be familiar with this picture of a wave, a water wave. In this case, what we have is a droplet that falls on a water surface, and it creates a vibration. In this case, it's vibrations of the water, up and down, and it propagates through a surface. You can imagine light like a very similar thing. But in this case, it's vibrations of something us physicists call electric field. That sounds a bit weird, but for us tonight, it's just going to be like a little arrow that is shaking. And instead of propagating in a surface, this propagates throughout the entire space. After, that reaches our eye, and that's what makes us see. But actually, I was counting to have 2 hands, but it's not happening tonight. So I brought like a laser pointer, okay? You hear me now? Yeah. So you can see it's green light. It's a laser pointer, so it has special characteristics. So let's try to think of it as a wave. How would this look like? So this is the laser pointer, amplified, and this is the wave. What us physicists, or one of the things we care the most about waves, is the distance between the peaks. So here, in the water wave, would be this distance. In this case, is this one. We call this wavelength. In the case of green light, like this laser pointer, this distance is 532 nanometers. And this is what makes light, or like the green laser, green. For example, the laser pointers we used before were red. What does this mean? This means that this distance is not like this, but a little bit longer, like that. If the laser pointer was blue, we would have it a little bit shorter. And that's really what makes the colors that you see every day. But, okay, you already heard a little bit of what a nanometer is. But how small is this distance compared, for example, to my height? For you to imagine, if I place myself here, this is to my height as I am to the diameter of the Earth. So this is really, really small. And how cool would it be if we can use this as the division of our ruler? Then we will be able to measure really, really tiny displacements. Well, this is what we do in the lab, and I actually wanted to do like a kind of a demonstration, and for that, I'm going to ask my lab mate Yannick. He was really reluctant and he didn't want to come tonight. Please, an applause for Yannick. Yeah, he's the best lab mate, and tonight I'm going to ask him to do the hardest task he's ever done, which is holding a mirror. So let's imagine that what we want to do is to use light to measure how the mirror is displaced. Now, here I'm going to exaggerate everything. We're talking about very, very tiny distances, but you don't actually can't see them. So we are just imagining that this is really tiny, okay? But we are going to exaggerate it. So how does this work in the experiment? So basically we need, as I said, a laser pointer. We have to watch out not to damage an eye here. So we are going to need two waves, okay? The one I'm going to send to the mirror, and then it's going to come back, and I'm going to look at the reflection. On top of that, I need a second wave. You kind of have to imagine that I would send a second wave to the wall, and then it will come back. The important thing is that the wall is fixed, and what is moving is just the mirror, okay? So let's imagine that Yannick is in that position, and I would send the light, and the light comes back, and then I look at the other wave, and these two waves meet together here, where my detector is. What's going to happen? So if the two waves are or come to me in a peak of the wave, they are going to add up, they are going to mix, and what I'm going to have is way more light. So I'm going to see a very bright spot on my screen, as you can see here, because the two waves are at the maxima, and they interfere, and they add up. Now, if Yannick moves a tiny little bit of a distance that's going to be a quarter of a wavelength, what's going to happen is that the waves are no longer in phase. So I will have one in a maxima and the other one in a minima, and they cancel each other. And basically what I see, it's just nothing. If Yannick moves a little bit more, now we end up again in the situation in which we have two waves on a peak. They combine and we see a bright spot. Thank you very much, Yannick. And you can imagine... You can already imagine this goes on and on as we displace the mirror. Now, I want you to focus on something. What do we see here? Bright spot, black spot, bright spot, black spot, bright spot. This looks very much like the divisions of the ruler. In a ruler, what do you have? A line. And you know that the next line is a millimeter of a distance. What we do know here is that every time we see a bright spot, we know our mirrors has been displaced by half of 532 nanometers, which is really tiny. Okay, so this for now. So I've told you that with the properties of waves and light, we can measure really tiny things. But light is way cooler than this, and we can do many more things with it. And the thing that I haven't told you yet, and one of the properties I like the most from light, is that actually light pushes. Yes, light pushes. And the reason it pushes is because light is not just a wave, but it's also a particle. I'm not sure if you've heard of this. Have you heard of this before? Yeah, okay. A lot of physicists here, but maybe other people haven't. So light is also what we call quantums of energy. And instead of a wave, what is happening is, if Yannick comes back, thank you, Yannick. So every time I'm shining light to Yannick, what I'm sending is actually little photons, or actually photons, which for us tonight is just ping pong balls. And these ping pong balls are actually impinging momentums that they're really pushing Yannick. But, okay, so for now, you've already heard, I think, five talks with mine. So you should start thinking already as physicists a bit. And now you would say, I'm not happy with this description, because the sun is shining on me all the time, and I'm actually not pushed. And right now, I'm starting in a very bright light source. I'm also not pushed. So what's happening here? The thing is, this force, or this light pushing us, is a very, very weak effect. For you to have an idea, just the fact that I'm pushing Yannick with this laser pointer could create a force which is the same as the weight of a bacteria. I'm not a biologist, but I know you're all surrounded by bacteria and you don't feel them, okay? So this is the same. So this effect is really, really, really weak. But I told you at the beginning of the talk that actually I spent most of my time in my PhD trying to measure things that I don't know how to measure. How could we measure this very weak force? Well, if I want this light beam to be able to push Yannick, the first thing I can try to do, sorry Yannick for this tonight, is send him to a marathon, make him run a lot and lose a lot of weight. This would be the first thing. If Yannick is light enough, at some point, maybe I'm able to push it. In reality, in the lab, what we do is we use things that have really low mass, and they are really, really tiny, so that we can actually see this effect. But I could also do another thing. Instead of just sending one of these ping pong balls or one photon, I could actually amplify this and send really a lot of them. So this is also what we do in the lab. We send a lot of light to enhance this effect. Thank you, Yannick, again. And okay, so we use light to push, and this is really cool. But can we do even more things with it? So imagine now that the mass, or Yannick, or the thing I'm trying to push is also able to swing. Imagine we have like a very tiny little swing, okay? Like a kid on a swing. And now we use light to push it. So we could use light to really, when we do it in phase, enhance the motion, as when you really push a kid until it goes away. But actually, please don't do that. What we can also do is send the light in a way that instead of pushing, what we do is slow the motion down. So you're basically out of phase. And when you do this, if you have something that is vibrating, you can, what we physicists call, cool it down. So you can really make it slower. So with this, I hope that tonight I convinced you that next time you open a toolbox, you can see light as a measurement device and something that can actually push. And I want to thank you very much for your attention.
So thank you, Irene, for this very insightful talk on how light influences